This project is CubeSats for climate change monitoring, supported under NASA EPSCoR. The work brings together faculty, staff, and students across HSFL, including Dr. Miguel Nunes, Dr. Paul Lucy, and team of students. This presentation gives an overview of our mission concept, our detector testing, and the path toward the future of interferometric long-wave infrared payloads. C3M's goal was to integrate an infrared spectroscopic payload with the Artemis CubeSat kit with the purpose of detecting and mapping greenhouse gases, supporting wildlife recovery, and improving on characterizing volcanic hazards. Our approach makes it possible to create a satellite constellation that not only has high spatial resolution, but has timely and precise monitoring while being cost-effective. The current 1U development and detector testing serve as the technical foundation for scaling into a more capable 3U platform, where expanded volume, power, and optical path length will support advanced interferometric payloads and higher performance environmental sensing. This is the Artemis CubeSat kit, a spaceflight-ready and educational 1U CubeSat developed by the Hawaii Spaceflight Laboratory, funded by NASA's STEM engagement program. The kit is designed to work for any CubeSat payload, and its design, integration, environmental testing, and operations are carried out by Mānoa. These are our two detectors that we use for testing, the FLIR-Lepton 3.5 and the Boson Plus 320. They're integrated with the Artemis CubeSat kit to validate our long-wave infrared data collection workflow and ensure the mechanical and electrical interfaces behave as expected. The slide also mentions associated optical advantages, but those apply to a future version of the payload. For now, our focus is strictly on validating the baseline long-wave infrared detectors and building out the 1U testing pipeline. After integrating the FLIR-Lepton into the Artemis CubeSat kit, we attached it to a drone to do remote airborne testing. We flew the CubeSat up to 100 meters and were able to confirm the integrated payload, avionics, radio link, and ground station operate together under real flight conditions, capturing and streaming thermal imagery throughout the flight. This included infrared pictures and a live stream. We also did long-distance testing with the same setup, which was a 1.6 kilometer ground link demonstrating image and live stream downlink, and the retransmission protocol. We achieved 99% data integrity and 72.2 kilobytes per second peak throughput over ultra-high frequency radio.
My glasses on right now, man.
Yeah, I'm gonna downlink in 5, 4, 3, 2.
Export.
Woo! That's sick.
That's actually really good.
That's sick. Let's go higher.
Let's try.
Next is our software-defined SNAC protocol. It is a reliable, high-throughput thermal data downlink for 50-byte half-duplex ultra-high-frequency radios, and it supports 160 by 120 long-wave infrared thermal image transmission. Includes a 45-byte SNAC bitmap acknowledging up to 360 packet fragments, minimizing retransmission overhead. For our bare metal version, the bitmap-based SNAC requests retransmit only missing packets. Field tested up to 1.6 kilometers as mentioned, up to 72.2 kilobytes per second. Our F Prime version brings the same selective repair concept into managed flight software. It goes as followed: scheduled capture, data product, CRC verified downlink, then ground viewer. Next up is our software demos, from bare metal radio transport to the integrated F Prime payload workflow.
All right, this one right here is going to be our bare metal demo running on the CubeSat over here. Right now you can see that we do have a dual payload set up with the Raspberry Pi RGB camera as well as the Lepton 3.5 thermal camera. So real quick, we're going to do a ping over here. You can see that we were able to get telemetry back upon from the satellite. Let's go request the status.
Like, my status?
Oh, I'm just going to do the status button up there.
Oh,
that's fine.
that's for the ground station.
That works.
Yeah.
Yep. You see the Raspberry Pi is on, and if you type in radio status, cool. You can see that we are getting 23 dB, which is very good inside the lab. So now I'm going to go take a picture with the dual payloads.
So I took a picture on the Lepton and I also took a picture on the RPI cam.
Okay, nice. And it's going to automate that.
So we can request a lepton image.
Requesting the lepton image now. Okay, see that header receive. This is our picture thermal camera, and that's me sending over the GDS right now. So now we request the Raspberry Pi camera, the RGB. Okay, should be downloading. And there you go. So you can see side by side comparison between a normal RGB camera right here and the thermal one. And that's a camera over there to our GDS over here. Hi, I'm Dennis. This is going to be our F Prime demo over here. We have JC over there holding the C3M satellite using the F Prime demo. And over here, I'm going to show you the ground station side. Right here, you can see the OBC, and you have our antenna right here. So terminal-wise, I'm going to start our ground station software. You can see that's our payload receiver, and then this is the F Prime GDS stock software. You see right here that we have an active telemetry link, RF, from this antenna, the ground station, to the satellite over there. And so I'm going to split this up into two. So one side's seeing the payload stuff, and another one over here. So you can see the events. So now if I go into base mode, you see that, hey, we're able to actually get events and telemetry from this. From here, I'm going to go into the state of health. You can see right now that we don't have a EPS, a payload, etc. But it's just to show like, hey, we're able to get comms. We have the comm system and it seems okay. So we're able to get telemetry and do command and handling from here. Now I'm gonna take a picture using our lepton camera. So we're gonna schedule collection in about 3 seconds. That camera over there will take a picture. So I'm gonna put my fingers up. 1, 2, 3. Okay. Scrolling down in the logs, you can see that image was captured and a science product is ready. And it's about like 40 kilobytes. So now we're gonna request the downlink. Okay, requesting the downlink, and you'll start to see the packets come in. It's about 10 seconds, so pretty fast. Cool, and that is us. You can see right here, the hottest spot using the lepton camera has a calibrated thermal profile, so it's able to actually detect the temperatures right here. That's your L, that's me. And you can see the hot spot right here is actually this GAN connector right here. It's my laptop charger. That's the hottest thing you can see right now. And one more thing we want to showcase is our live stream feature. And so if I go back over here and start a stream, I move into the live stream over here, see nothing's there, but if we start a stream, you should see a little blinking of us. So if I start raising my hand over here, it's about every 10 seconds or so. JC over here, maybe put 2 hands up. A little bit here and there, but you know, it is possible to have a live stream using very cheap hardware that we're having right now. See, so that's Gerald's hand over here. And that's our demo.
Thank you. Feel free to reach out to the C3M team.